All right, so this trend of electronegativity really is, give me your focus here, everybody. It's like the root cause of why some things are ionic and some things are covalent, and then we'll also learn about metallic. It's all about, because electronegativity is all about the force, right, at which if I'm an atom, how powerfully can I pull on another atom's electrons, right? We know the trend, as we learned last unit, goes from low to high. We leave off this column because they don't really bond, and so they don't really have electronegativities. And so the farther away here it is, the way I think about it is they're the buffer element when it comes to pulling electrons. These ones sometimes don't even hang on to the rope. They just let their electron go, okay? So as we look at this, we saw this idea of a pull of the electrons, and it brings up a new big vocab word of polarity. So polarity results when there's a tug of war on the electrons in one direction. Yeah, Levi.
What would happen if you combine fluorine and francium? Would it explode, or would it just like poof?
They would bond. It probably would put out a lot of energy. So I don't know if explosion sort, but it definitely probably put out a lot of energy because of how like reactive they are. Yeah. Like when you mix, like, so for example, like chlorine and sodium, when you mix those two, which are like same family, it produces a super bright light when they react. So I'd assume that that one would be even bigger. Yeah, because it's like that one pulls so hard and that one like doesn't even hang on, right? So with this idea of polarity, okay, polarity is that shift in the electrons in one direction. I think of the word polar, you can relate it to like the north and south poles, right? That there's a positive side and a negative side. That is because of the electrons not being shared equally. If it's not pulling, non-polar, then it's shared equally, okay? It's still being shared in both cases. If something's polar, they're still sharing the ice cream. One just gets less licks than the other, okay? If it gets so extreme that they're not sharing anymore, then that's when it transitions to an ionic bond. So that's kind of like, here's kind of a scale of the transition. So if they're sharing equally, it's non-polar covalent. If they're sharing but it's not equal, it's polar covalent, and then not sharing at all is ionic. Okay, so kind of the transition of how it goes. So our first objective here is being able to predict what type of bond is going to form when two things connect. And it's all about this difference in electronegativity. If there's a big difference, it will be ionic. If there's a little difference, right, then it's going to be covalent for sure, and then depending on it, if it's polar or not. Okay, so this results in a positive side and a negative side. So we're going to use this word polar a lot in this unit. So anytime you hear the word polar, think positive and negative. There's sides of it because of that shift in the electrons overall. We're going to show you how you can model that or how we represent it symbolically. Okay, everyone okay? All right, so there's two ways we represent polarity on a bond. There's this method, which uses this fancy Greek symbol that stands for a partial. So this stands for partially positive. So that's what that symbol is there for, is to say it's not a full-on positive. Because full-on positive means we're not sharing ice cream anymore. They're still sharing. See the line? That means they're sharing. But because fluorine wins in the tug-of-war, it's going to be partially negative, and the thing left behind will be partially positive. The other way, so these are the same symbols. So really, if it doesn't tell you which one, you can pick which one you like best. The other way to represent this, which your cartoon did, is using this arrow, which is called the dipole arrow. It's kind of like cation, where you like would read it as cation. Like a lot of people read this dipole. Which I don't blame you if you've never heard it before. But you pronounce it dipole because di means two, and it's two poles, positive and negative. So the arrow always goes towards the one winning the tug of war, or aka the higher electronegativity. Whichever one has the higher electronegativity pulls the electron And the thing left behind is going to be left positive because you've removed the negatives. And so that's why we put like a little plus sign on the tail of the arrow. So once again, this and this represent the same idea, it's just two different notations. Okay? Questions on our symbols? Now, the greater the difference, the bigger the pole is going to be, right? Once again, if you have something over there and something, but it's not quite ionic, you can have what is known as a really big dipole moment. So the bigger the dipole moment, the more of a shift that's happening, meaning almost to be ionic pretty much, but it's not quite ionic yet. And if the dipole moment's low, then that's almost where it could be more nonpolar than anything else. So once again, that dipole moment is just describing that shift in the electrons. Now there is like a mathematical way you can do this where you can actually get a chart of electronegativity values, and you can look up, okay, fluorine I know has electronegativity of 4, I think carbon is like 2.0, and you can subtract them to find what's the difference and then classify the type of bond based on the difference. Honestly, the only way you can do that though is you have to have the data values, and so a more practical way is actually just using a pattern found on the periodic table that's sorted by metals, nonmetals, and metalloids. So I gave you this periodic table, but it did not print it in a shade that I was hoping it would, so there's no difference between them. The biggest thing I need you to outline right now is this pink box. Just draw out that dividing line, because then everything to the left is a metal. If you have colors, you can use that, not just shade it out. Everything to the right is a non-metal. And based on this classification, it kind of sorts out what's going to go on when the two interact with each other. Now, it's up here as well. I've had it taped off on my periodic table, so you kind of always will have it as a resource throughout the year because I'm too lazy and I don't want to take off my tape and put it back up every time you guys take a test. But just FYI, like on the AP test, like you're not going to have it marked out for you, so you do need to know where that line is, but hopefully after looking at it for like, you know, yeah, like all the days we're in here, you'll kind of just know where it is. Yeah. That's kind of just, right, if you stare at something long enough, you just remember it. But you do need to know where that line is eventually. So metals all fall in the category of low electronegativity. They don't hold onto their electrons very tightly. Non-metals hold on very tightly, and the metalloids are kind of a weird both group. Yeah?
So with your periodic table, it has PO in there, but on that one it doesn't?
Yeah, great observation. It's debated. Like if you Google it, like some places say it's a metalloid, some say it's a metal. I think because it's super radioactive and so it's not very stable, so I don't think we have a lot of data on it, maybe to classify officially what it is. So yeah, that's why on that one.
Will
yeah,
it ever be used in the question?
No. Yeah, you won't really ever see. Because once again, we don't really use it in like practicality, besides like in like atomic bombs and stuff like that. But
Yeah, it's America.
any other questions on this chart before we try some practice problems? Okay, so if a question were to ask, what type of bond exists in this compound, you're looking for that difference in electronegativity. So I need to find these things on the periodic table. So the first step would be find calcium. So calcium's number 20, put your finger on that. Okay, so that one is classified as metal, non-metal. Which one?
Metal.
A metal. So calcium is a metal. It's bonding with 2 chlorines. Right now, the numbers don't really matter. It's just what is it bonding with. So is chlorine a metal or a non-metal?
Non-metal.
Good. So we have a metal bonding with a non-metal, which always results in an ionic bond. Because you have low electronegativity with high electronegativity, the ice cream's just going to get passed over. Maybe the penguin didn't even want it in the first place.
Towards the chlorines, correct?
Okay? Say that again, Bryson.
Towards the chlorines. The electrons.
Yeah, so chlorine's going to take it. Yes. Okay? All right, let's do this one. So then same thing, find them on the periodic table. Phosphorus is a non-metal. Oxygen is a non-metal. So when you have two nonmetals, they both have high electronegativity, so it's like two polar bears. It's going to be covalent. They're not going to give them up, so they're just going to share. Because they both really want their ice cream. Okay, try 3 and 4 for two smiley faces. You can talk to your table buddy. Yeah. Not right now. We will get to that, but for now, just if it's ionic, it would be. So do 3 and 4, and then set your pencil
Wait, what happens
down.
when you have three things?
So you can't have 3. It just still follow the patterns. If it's all nonmetals, it's going to be covalent. If there's any combination,
So is a metallic bond? What is it?
so covalent, oh, you wrote this wrong. Oh wait, so ionic is metal and metal, metal and non-metal. Covalent was two nonmetals. There you go. Alright, I'll give you 20 more seconds and then we'll check these two problems. Right now we're just starting with ionic, and then we'll dive into
It's Tuesday. There we go.
Okay, this symbol I'd like you to show me for your answer. Once again, hold it near your heart so it's not like so everyone can think for themselves. Is show me a C if you think it's covalent, or an I if you think it's ionic. Okay? Alright, number 3, show me what you put. Number 3, what did we pick? You said covalent, have a smiley face. Good job. Now this one has a tricky element. What's tricky about this guy? Or what's in there? There are 3, so you gotta look at all 3, and then, why is hydrogen tricky? Yeah, he's the adopted one. He's a non-metal, but he's on the metal side. So make sure if you didn't note that, like on your little staircase thing, that hydrogen is a non-metal. Okay, very good. All right, and then 4, show me what you put. 4, what do we put? Ionic or covalent? I guess I'm telling you that's not an option right now. The answer is ionic. Good, if you said that, have a smiley face. Right, so sodium's a metal, non-metal, non-metal. So anytime a metal gets thrown into the mix, it pushes it ionically, right? You can have lots of things in a compound. You can have like 7 things, but if they're all non-metals, still covalent. Okay, questions on these problems? All right, the other way we could look at it is, same concept, just adding a different component, is looking at a bond, identifying if it's ionic, covalent, or metallic, but then indicating what the electrons are doing. So I'm going to do the first 2, and then I'll have you try the next 3. So, same thing as we just did, find them on the periodic table. So sodium's a metal, bromine's a non-metal, so I know this is going to be ionic. Then the second part is showing who's taking the electrons away. So who wins in the tug of war between Br and Na? Bromine. Because as we go across, right, electronegativity increases, so bromine will be negative, and sodium will be positive.
Do we do the arrow thing?
No, because it's not a partial, it's a complete takeaway. Yeah, great question though. With this, it actually with ionics will always be the metal's always positive, and the non-metal's always negative. Just because of the difference of the periodic table every single time. Okay? Alright. This one is a non-metal with a non-metal, so what type of bond is that? Covalent. Now, like Levi brought up, since it's covalent, now we're going to use the arrow to show the shift, because it's not a partial, I mean, it's partial, not a full. So So who wins the tug of war between O and H?
Oh.
Oxygen does, so we're gonna draw the arrow towards O with the tail. Questions on that? Yeah, Jean. So the trend of electronegativity goes from left to right and up, so it's whichever one is closest that way will always win the tug of war. Does that help? Yeah, good question, Jake. Jeff.
Is it like a trend that all the ions are going to be complete and all the covalents are going to be partial?
Yes. Yep, so this should never pair up with ionic. Same thing, this would never be with covalent. Otherwise, you're like labeling it incorrectly. Yeah, good pattern. Okay, try C, D, and E with your table, buddy, for 3 more smileys. Ready, go.
Yeah, so with the CS being positive.
And it's copper, right?
So that would be.
You like my
Wait, why is the polar bear?
Because I didn't go to packets, my pencil went right, and I turned it
I like that.
Mine's under.
Oh, thank you.
I should just.
I wanted to write.
I like it.
Oh, yeah.
Okay, same thing. Show me C or I based on what you think it is. Or we do have an M option now. Metallic. Okay, so C, show me ionic or covalent. What'd you put?
Or metallic.
Or metallic. Sorry. Good. It is covalent, so you should have drawn an arrow like so. If you have that, have a smiley face. Okay, show me for D, how did we label it?
Plus, minus, ionic.
Good, so it is ionic, and you should have positive, negative, like so. Questions on that one? And then the last one is kind of, yes, I was being tricky. I did it on purpose just to get you thinking. So this one, you should have said it was a metallic bond.
Yeah.
Oh, I didn't know that we had that.
So what type of, how do I know it's not ionic or covalent? Yeah, so it's the one scenario we hadn't addressed of metal with metal, which the name is the easiest because it's named after them. With this one, there really is no labeling of what's going on here. If you tried to do something, that's fine. But if you said it was metallic, have a smiley face. We'll kind of talk about why there's not a label there. So, questions on how to do this? Yeah, I don't know. Yes. So the metallic ones are kind of weird in that it's not like charge is weird. So there's really not like, they haven't come up with a symbolic way like this in a metallic bond. No, so you just label as metallic, but there's nothing to show what the charge is. And we'll kind of see why it's kind of weird what goes on there. Okay, what we're going to look at now here is going through our 3 ones. Okay, we just covered. Nice long So we just hit this side of the triangle symbolically, right? But if I give you a symbol, NaCl, you should be able to say, oh, that's an ionic bond. Now, let's go deeper into the molecular side a little bit of what's going on down at the molecular level. Okay, so we already addressed this with 2 of them. So what are the electrons doing in an ionic bond? There is a hand, someone help us out here. Go ahead, Garrett.
So basically one of them has like a lot more electronegativity, so it takes one of the electrons, or it takes the electrons,
Perfect.
and the other one gives them away.
So one of them, so like, takes the electrons away, right? They both get what they want because one of them gets a full outer shell. The other one emptied a shell, which then makes it full. Why does the polar bear and penguin still like stick together though, Jack? You know? Like if I take your ice cream, why are you gonna still hang out with me? The hope of that they'll do that. Any thoughts of why? Why would the penguin still hang out with the polar bear after its ice cream? No, but good thought. This might be that. Dylan, you want to help
Because
him
one's positive and one's negative, so they
out?
attract.
The penguin becomes positive, the polar bear is negative, and positive and negative things do what?
Okay, I don't know, I feel like the penguin might also show not be negative.
It does feel a little backward with the analogy here, so. Okay, so add this in. Alright, so electrons are transferred between atoms with a large difference in electronegativity. Something high, like Garrett said, with something low, the electron gets transferred. Okay, the ice cream is taken away. Once again, you can kind of, I guess, assume maybe penguins are lactose intolerant. They don't really like ice cream. So it just gives it away in that case. I do also, I don't know. Garrett, have a smiley face, by the way, if I didn't say that already. Okay, and then what type of elements make ionic bonds on the periodic table? Yeah, metal with non. Right, something from the left side with something on the right side.
Unless they develop lactose intolerance.
If we could magic school bus into an ionic compound, it would look something like this, where you have the positive thing that lost its electron, the negative thing that gained the electron, but it's like this massive network because it's all positive and negatives. And so they're going to be attracted in all ways. You actually really can't tell which one gave up its electron to it because it's just all magnetically connected. So this is like what a salt crystal would look like at a very small level, where this is the Na and this is the Cl. So that's table salt. NaCl, NaCl, NaCl in 3D space. Okay? Okay, questions on ionic bonding? Okay, covalent bonding. Someone might raise a hand, help us out. What are the electrons doing in a covalent bond? If I raise a hand, help us out here, Bryson. What do they do?
I said that the electrons are equally distributed between the 2 atoms.
Equally distributed between them, or we'd say like they're shared between them, right? So in a covalent bond, yep, the electrons are between it. It is something the cartoon doesn't quite show well. With a covalent bond, it's a I share with you and you share with me. It's not like a one-way share. It's I'm going to put one in the middle, you put one in the middle, and now they belong to both of us. Just like that overlap picture showing, apologize if you can't see blue-green difference. But so the green one gives one, the blue one gives one, and so they now belong to both. Okay, now as we mentioned, it's not always shared equally. Sometimes one of them might get them closer to it than the other, but if it's covalent, they are shared. Now, the reason why covalents are going to take most of our unit is because there's so many ways sharing can happen. This is in a sense what we'll learn how to draw later on, is a picture of that sharing relationship. where the lines represent, I share one with you, you share one with me, they're shared between us. If there's two lines, it's I share two, you share two. In this case, it's sharing in different ways, right? But there's a lot of different ways sharing can happen, and so there's a lot of variety to covalent compounds. Okay? And the reason why they're sharing is because they have high electronegativities, right? They're all polar bears and nobody wants to give it up. And so to make them satisfied right from the beginning, they're just going to share. Right? Because remember, the reason why they're bonding in the first place is to get a full shell. And if they can't get a full shell, they're not going to bond. So they're going to find a way to get there. The electrons are shared between two atoms.
Metals are so silly, man. That's why they're so bad. That's why I dropped them.
Okay, questions on covalent? Yeah. Yeah. Yes. Yep, so when you draw, so when we learn how to draw Lewis structures, it's only for covalent. Because if you were asked to draw an ionic structure, you draw the positive, negative, right? Which actually can get quite complicated too in some ways. We actually don't get into the details of those, but yeah. No, good connection, Jack. Okay, everyone good here? So then our last one we're going to look at is metallic. Okay, so with metallic bonding, do metals hold tight to their electrons or loose to their electrons? Loosely, right? So metals don't typically, neither of them are really pulling on each other if you have two metals that are bonding, right? Or even a metal bonding with itself. The other problem with metals is they don't have very many valence electrons to begin with, right? They have 1, 2, and 3, right? Some have 4, these metals down here. But they don't have very many valence electrons to begin with. So they run into a problem of, okay, I have some, you have some, but us together doesn't make 8. And that's what they want, right? They want 8 valence electrons. So metals do a type of shared idea, but it's different from covalent because in this case it's a let's all share and pretend we have enough. Okay? So this picture here is representing what is known as like the electron sea. That's what sometimes we nickname with metals. There are really not that many valence electrons. They each probably came with 1 or 2. But the electrons are in constant motion, and so if we pass the ice cream fast enough, we'll all feel like we have ice cream.
Yeah!
That's what goes on in a metal bond. Great model. Okay, so the electrons flow freely throughout the atoms because they all have low electronegativity. But really, like if you were to pause it, like if you could freeze the electrons in time, like they wouldn't all have 8. But it's kind of like a fan idea. I think of like a fan spinning. Like while it's on, it looks like it's filling the space completely. But if you stop the fan, right, there's distinct blades. So it's kind of the same idea. And then obviously this one's the easiest by name. This is when 2 metals bond with each other. Questions on metallic bonding? I once heard that metallic bonding is kind of like communism.
Communism.
I'd say
Okay.
covalent. Yeah, at least polar covalent.
Okay, any questions? All right, what we're going to look at now is we're going to start, so we hit this side of our triangle really hard today. That's the big one. Your homework assignment 2.1b is all about that symbolic. If I give you 2 chemicals, you tell me if it's ionic, covalent, metallic. Show me the arrow, the plus, minus, so on and so forth. Okay? 2.1a, we're going to get started on right now in our lab groups because it's going to start connecting us to the top side of it. Okay? So I'm going to you don't have it yet in case you're looking. So I'll pass out your homework packet, and the first thing is going to be this 2.1a. Once again, we're working on this right now. You should be able to get it done before the bell rings as a lab group. And then you'll only have 1 more assignment. Okay? Our goal here, as a lab group, is you're trying to determine what patterns are there between ionic, covalent, and metallic when it comes to things we see with our eyes or things we measure. That's the goal. The big picture is on Wednesday, your lab is going to be, I'm going to give your lab group 4 cups of some random substance. You'll go into the lab, you'll pick whichever test you want to do, and you have to come back and tell me this one's ionic, this one's covalent, this one's metallic, or whatever it is, based on the data you gather. So today's goal is to identify what patterns can we find. So let's go through our test really quick just to define some words you may not know. So the first 2 are just looking at the substance. What can I tell about it? So if I just look at it, shape-wise, is it a regular or irregular shape? Luster is like the shine of it. So if it's really shiny, it has a high number. If it has like no shine, like aspirin, you know what aspirin tablet looks like, not shiny at all. Okay, but aluminum is very shiny. Okay, so that's that test. Pretty simple test, but still a test of observation. Okay, another test that you can perform. Now, when I say you can, you don't have to do all the tests next time. You just have to come to a conclusion. So as you're kind of working as a lab group today, you'll maybe identify, oh, this test is really good for identifying metallic, but it's not very helpful for identifying covalent. And you can kind of narrow down, and it will prevent you from having to do all tests for all substances. Okay? This test right here, solid conductivity, is we're seeing does it conduct electricity as a solid. So when you do this test, you'll have this right here. It's a conductivity meter. Okay, pretty much it's just the idea of complete the circuit. So we have a battery here. 2 prongs. No, it will not electrocute you, in case you're wondering. Okay. But what it does do is when you put it in a substance that is conductive as a solid, the lights will turn on because it's completed the circuit of the battery. Okay? So for example, if I wanted to know if this substance right here conducted as a solid, I just put, now you have to get like a good connection, which yours will be in cups and it's a little easier. This last period. That's probably gonna not work for me. Oh, do you see it? Are you seeing that? Okay, the light's flashing. Sorry, I'm blocking that side. Okay, well, should have brought a better sample. But the idea is you'll put it, you kind of have to surround it for it to like get a good feel. But if you put it in the cup and it doesn't light up, then it's not conductive. If it does light up, it is. There are ranges of like, on the back there's a scale of if only one light turns on, then it's like partially conductive. But that's what, when you read that test, that's what it's telling you. Okay, is solid conductivity. Yeah, Levi.
So is that like those big metal ball thingies where you like line up and you like are holding hands and then you touch the ball?
Yeah, very similar idea. Yep, is you're just connecting the circuit and carrying it. Yep, and then you get shocked, right? Yeah. Okay, all right. Malleability is the ability of something to be shaped without breaking. Okay, so something with high malleability, like aluminum, right? You can bend aluminum foil very easily and it doesn't break. Okay, if you tried to bend an aspirin tablet, it's just going to break and shatter. So that's what malleability is. Once again, clay, very malleable. Granite, not malleable, right? Just shatters. Okay. Melting is another test you can do where you put it on a hot plate and see if it melts. Now, our hot plates aren't scientific enough to tell you like the temperature it's melting, so we're going to measure it by time. Some things, our hot plates don't get hot enough to ever melt, and so that's what this means, is it must have a high melting point because it never melted. This is referring to how quickly it melted. So this melted within 10 seconds, this melted within 25 seconds. Now to help you in analyzing your data, I have looked up just online the actual melting point of the substances as well. When you do it, you won't have this, you'll just do the test. Because you won't know what the substance is, so you can't Google what its melting point is. Yours is just going to say cup number 1. Okay? All right, solubility in water is does it dissolve or not? So if I put it in water, will it dissolve or not? Okay? This is aqueous, that's that word. Aqueous conductivity means does it conduct if it's dissolved? Okay, so meaning if I put it in water and it dissolves, does it now conduct? Now with this one, there's a very big misconception out there in the world we need to understand. Water does not conduct electricity. Okay? So if I put this in a beaker of distilled water, it will not light up. Water does not conduct electricity. It's what inside the water that causes it to conduct. So yes, the ocean is very conductive. Don't be like, oh, I can go swim during a lightning storm. Don't do that. Okay? Because there's things in the pool that make it very conductive. Okay? But some things will dissolve and not make the water conductive. So that's what this test is showing. Does that make sense, the difference between aqueous and solid conductivity? Now, if something doesn't dissolve, like this, like it's always going to be 0, because if it doesn't dissolve, you can't have aqueous conductivity. Because this is about, does it conduct when it's dissolved? Okay? And then I've given you the chemical formula. So your first objective will be, as a group, is, well, since I have the chemical formula, we can label what type of bond it is. From there, then you can sort them out and see, okay, what patterns are there between ionics, covalent, and metallic. Okay? So I'll pass this out to you, and I'll tell you who you'll be working with for your lab group. Okay? So what I want you working on, so first step is just fill out this. Then once you have that data, you can work on the questions on the back, which kind of guide you through what are the different patterns you can find. And then if you happen to get that done, this I want you to get done as much as you can before the bell rings, which you should be able to. Then you can start working on 2.1b as well. Okay? Any questions for now? Okay. Alright, so you 4 will be a lab group.
Don't pass it to him. Don't pass the papers to him.
Thank you. Yes, no, we're going to turn it to me. You 4 will be a lab group this time.
A lab.
You 4 will be a lab group. So, by the way, you're in a lab group, so you can like divide up the work right as you're doing it.